Hello, welcome to our series of lectures about equilibrium. This lecture will be discussing the ice table exercises. And we have a problem here that we're going to go over it today, and it's about the ice table itself. So, reading the problem, this is 1980s. CFC11 was one of the most heavily produced chlorofluorocarbons. The last step is in its formation is CCl4 gas plus hydrochloric acid gives you CFCl3 gas plus hydrochloric acid. If you start the reaction with equal concentration of CCl4 and hydrochloric acid, you obtain equal concentration of CFCl3 and HCl at equilibrium. Are the final concentrations of CFCl3 and hydrochloric acid equal if you start with the unequal concentration of CCl4 and hydrochloric acid? And obviously explain your answer. So it's kind of lengthy question, so it's gonna boil down to a few steps. And so let's start with highlighting our main keys here. So it tells you in the question you obtain equal concentration of the products at equilibrium if you start with equal concentration of the reactants. But the question itself asks if you start with unequal amounts, will it still the same or different? So this is pretty much what the question is asking us to do is, will the concentration be the same if we start with different concentration of the reactants? So in other case, so if the concentration of CCl4 is not equal to the concentration of hydrochloric acid. So in essence, that's what the question is asking for. So if these concentrations are not equal, will the equilibrium hold and we get the same concentration? I mean, the equilibrium is going to hold, but will we get the same concentration of the products, which is the hydrochloric acid and the CFCl3? So let's figure this out. So the way they do it, I mean, there's a lot of explanation, and there's a lot of people say like it's gonna be. So through my career of teaching and tutoring chemistry, I get the two perspective, which is yes and no, so equal and not equal. But in this case, we're gonna dissect it in a way that is gonna show you why it's not this way. So let's start with writing the ice table and the concentrations. So we grab a yellow color. Okay. So start with the word ice here. So you know, ice sound for initial, C for final, change, E for equilibrium. So at initial, we're gonna use arbitrary numbers, and we're gonna have two cases. Case one is, what we're gonna do now is CFCl for concentration is bigger than the concentration of hydrochloric acid, sorry. So the first case, we have that the CCl4 is concentration is higher than the hydrochloric acid concentration, and since we know the coefficients of the stoichiometric coefficients of each one of them is just 1, so if you put one here, one here, one here, so we know it's 1 to 1 molar ratio. So we're gonna now assume some arbitrary numbers. So let's say that CCl4 is equal to twice, it's concentration obviously, the concentration of HF. So if we start with 1 molarity in terms of concentration of CCl4 is going to give you 2 molarity of, this is going to be, sorry, it's not 2 molarity, it's actually half of that for hydrochloric acids. So if we have 1 molar, if CCl4 concentration is twice at hydrochloric acid, so if you start with 1, it's going to be half. So go to the ice table, and we assume that, or we write them in the bottom, we should write them in the top, but you can write them in the bottom the species or the reagents. So let's start. So we have CCl4 HF hydrochloric acid, and we have CFCl3 and hydrochloric acid. So for initial, we said we have, let me use the color, let's go back to yellow. So we said for initial of CCl4 we have 1 molarity. Wow. Just fix this real quick. We have just 1. And for HF we have hydrochloric acid, we have 0.5 molarity. As you assume it's all in 1 liter, so it's going to be moles equals molarity in this case, if it's 1 liter. So, and here we have Y's for the products, Y1 and Y2. So now we need to know what's the limiting reactant in this step. So since all are 1-to-1 mole ratio, we just need to look at the one with the lowest number of moles or concentration, which in this case will be the hydrofluoric acid. So hydrofluoric acid in this case is the rate determining step, or the, we just put the limiting reactant. The limiting reactant. Okay, so I just put an arrow, small arrow here, so it tells you that it's this limiting reactant. So which means it's going to be fully consumed, or almost fully consumed. So the change will be minus, I was going to confuse other people, so I just put this in moles. So we consume the whole moles, assuming here we're using 1 liter solution, and you end subtracting from the, so if half moles of the hydrofluoric acid reacts with half moles of the CCl4, you end up with losing half of what you have of CCl4. So you end up with getting 0.5, you get 0 here, and here obviously getting addition of 0.05, 0.05, oh sorry, and in the addition of 0.5. So we know the initial concentration of Y1 could be 0, could be something else, but just for the sake of the argument we can assume these are at 0. So you write here, let me erase this now. For the case, this is, by the way, it's case 1, so let's get rid of these. So this is case 1, and we know that Y1 equals 0, Y2 equals 0, as in the initial concentration of them are 0. So we're assuming that we don't have any of these in the beaker or the flask before the reaction. So when you add 0.5 to zeros, you get just 0.5, and then it is moles, Okay, so from this we notice that y1, y2, or the moles of CFCl3 and hydrochloric acid are equal. They're both 0.5 moles. The reason being is because everything is 1-to-1 mole ratio. So that's what answers pretty much the essence of the question. So they like right on hit like right on the nail of the question. So we're done the question. So since it's 1-to-1 mole ratio in every single reagent or product and product in the reaction, since they're all 1-to-1 mole ratio, it doesn't matter if they're different. They're still gonna be equal, even if you start with different hydrofluoric acid than the CCl4. You're still gonna get the same amount of product. And the reason being, let me highlight it. One second. So the reason that why we have this is because of the rate limiting reaction, which would dictate the reaction or the equilibrium. So now let's reverse it and do case 2. So case 2, in case 2, we assume that, let me just erase this now. Let me erase everything actually. Bear with me a second here, so let me erase the last thing here. So, in case 2, we assume that hydrofluoric acid has higher moles or concentration than CCl4. So in this case, we are gonna use the arbitrary one again, and think it's about as it's twice as big as this. So we start with 1 here, and this is gonna be half. So we're just reversing the whole scenario, and you end up with y1, y2, which is r0, and you end up with subtracting. The change will be the limiting reaction, which is 0.05. And here, since product, you're gonna add this amount. So you end up getting what in this case? So this is, you get 0 here for the CCl4, you get 0.5 here as excess for hydrofluoric acid, you get 0.05 for CCl3, CFCl3, and you get 0.05 for hydrochloric acid. So if even in case 2 scenario 2, you still get the same concept, they're equal, because it's 1-to-1 mole ratio, and the later unit step in this case will be the CCl4, because it has lower mole. So in a nutshell, since everything is 1-to-1 mole ratio, is going to be equal no matter what the concentration are. And if you start with 1 and 1, you're gonna, if they're equal, you're gonna get the best reaction or the most of it, because everything will react with each other to the full extent, and you get the most out of it in terms of product. So if you start with 1 here and 1 here, you end up with losing both of them and adding 1 moles of the products. So this is a basic question and basic usage of ice table and in studying the concept of the initial concentration change and the equilibrium concentration. And just to keep in mind, this molar ratio will play a big role in your equilibrium, in the shift and everything, so just bear that in your mind. And see you in our next video.